All right, so moving into more of our osmotic properties. So osmosis is the flow of a solvent, a liquid over a semi-permeable barrier. So again, this is the kind of thing you might have taken a look at in your biology classes. So first up, we have an isotonic solution. So this is that perfect solution that we were trying to get to with that osmotic pressure. What it says is we have the same concentration on both sides. So the dots that I have here are trying to approximate concentration. And we do have some flow across the barrier. For every one molecule of solvent that comes across, one molecule of solvent goes back the other way. So it's a nice, even, steady flow. Neither one of these is gaining solvent and neither one of these is losing. So we say there's no net flow. But by net, what we mean is there is a little flow back and forth, but neither side gains or loses. Every time one molecule moves to the right, one molecule moves back to the left. And this is our perfect solution. This is the solution that we want our cells to be bathed in. So these are happy, healthy cells. So on the left, you see an actual image. I believe it comes from an scanning electron microscope. The middle and the right side, of course, are drawings, but there's no net flow of solvent. So for every one water molecule that maybe crosses into the cell, one crosses right back out. So this allows the cells to maintain their shape. And this is the perfect solution. This is what you want all of your cells to be bathed in. Next up, we have a hypotonic solution. So this is when the outer solution is less concentrated than the inner solution. So earlier I told you that the way we have our solvent flowing will always be from less concentrated to more concentrated. In terms of a hypotonic solution, what that means is your solution is going to flow inwards. So it's going to flow into the inner chamber, which could be a red blood cell or it could be something else. But it's flowing inward with the attempt is going to be to dilute the inside and to concentrate the outside. So if you think of what's going on as it is always driving towards equality. I'm going to go back to the previous slide for a moment. It is driving towards this. We want the same amount of solute on both sides, same concentration. So whenever there's an imbalance, we get this osmosis where solvent is trying to flow. And in this case, the solvent is flowing inwards, again, to dilute the inner chamber and to concentrate the outer chamber. But I think the easiest way to remember it is this right over here. So we're always flowing from less concentrated to more concentrated. So from the less to the more concentrated. So when that happens, the inner chamber starts to swell up. So in terms of a red blood cell, this is when that membrane starts to get stretched and starts to have problems. If that inner membrane could handle it, the solvent would flow in. It would start to fill up the inner chamber until everything has the same concentration, and then everything's good in the world. But that means that this membrane right here has to be able to stretch. It has to be able to accommodate all that extra solution. And if it can't, then that's where we have our problem. So in the hypotonic solution, we are less concentrated outside. So when we talk about isotonic, hypotonic, or hypertonic, we're always talking about the surrounding solution. So hypo means less. So if you think of hypoglycemic, that is somebody who has low blood sugar. Hypo always refers to less, and here we're always referring to the surrounding solution. So again, the surrounding solution is less concentrated, and we get a net flow into the cell. So here all the water is coming in, and here on the left side, this is another actual image of a red blood cell, and you can tell that's not what red blood cells are supposed to look like. Here it is bloated, it has way too much water, and if the water keeps coming in, it will burst. And you may have heard of something called water intoxication. I know that sounds really funny that you could get drunk off of water, but there were some famous examples, and one of them was a football coach who tried to be really healthy, and he said, you know what, you guys, you're working out, it's hot, it's sunny, and I want you to drink pure water because pure water is better for you than all these sugary drinks. So he started giving his athletes just pure water, but they were sweating out salt. So what ended up happening is they created a hypotonic solution. The cells of these athletes were starting to swell up and burst. And where we saw this especially was actually in their neurons, their brain cells. And so they started walking around and stumbling as if they were drunk. And so that's why we called it water intoxication, because they looked intoxicated, but all they had actually done is drank water. So this is something that if you've ever been out hiking, you're really dehydrated, and you try to drink water, sometimes you'll actually just vomit it back up, or sometimes you'll drink it and you'll be like, ugh, gross, like I'm really thirsty, but I can't drink water right now. That's your body saying, hey, hold up, you're creating a hypotonic solution. So your body has natural defenses to tell you, hey, I'm thirsty, but this stuff, no, go give me something else. So that is to prevent this hypotonic solution. So let me see if I can switch over. I have a great video here. There we go. Okay. So any questions on those hypotonic solutions? All right, so next up is the opposite. These are hypertonic solutions. So this is when the outer solution is more concentrated. So remember, whenever we're talking about these types of solutions, we're always focused on outside here. And you know the word hyper. If your kids are running around like crazy, they are very hyper. They have too much energy. So hyper, think of it as too concentrated. So the outer is now become too concentrated. We still have the same rule that says the solvent flows from less concentrated to more concentrated. So here, solvent's going to flow outward. And just like before, the idea is to dilute the concentrated solution and to concentrate the dilute solution. So that's why the solvent's going to move outwards towards the more concentrated outer chamber here. So we're always driving towards having them the same concentration. Now, just like before, once the inner chamber, if we think of it as a red blood cell, that red blood cell starts giving away its solvent, that affects the membrane here. Last time we talked about that membrane expanding. Now we're going to talk about that membrane shrinking as it loses its solvent. So here on the left we have the before, and our solvent always flows from less to more concentrated. So in this case, it needs to flow outward. But when it does, this inner chamber starts shrinking up. So when I put this together, I just made a nice uniform shrinking, but that's not how it really happens in the real world. Things don't shrink up uniformly. They shrink up, I kind of want to say in a lumpy way, but those of you who have seen cells crenating, you know they look very strange, and I'm going to show you that in just a moment. So here, we're talking about our hypertonic solution, and the outside solution, the surrounding solution, is more concentrated. So this time it is the cell that has to donate its solvent to the outside. So this is what's happening when you are dehydrated. So as you are dehydrating, your cells are donating their solution to the extracellular fluid. This is very drastic though. If you're just like, oh, I'm parched, your cells aren't this bad at that point. But what you see here on the left, this is an actual image of a red blood cell that has crenated, it has donated its solution. So let me show you another image. Here's a great image, and we see on the right hand side here you have a regular red blood cell, and here at the bottom left you see a crenated red blood cell. So you can tell here in this crenated red blood cell that it is not going to be very effective at carrying oxygen. So this one down at the bottom is the result of being in that hypertonic solution where it has lost much of its solvent to the outer solution. And these images are taken by an SEM, a scanning electron microscope. And here we see a whole collection of these crenated red blood cells. So they're very interesting looking. You can tell they wouldn't be very useful inside the human body. We don't want anything that looks like this in our bodies, but they are fascinating to look at. So these are the result, again, of a hypertonic solution. So when you have a solution that has a very high level of solutes, so this could be something like a brine solution, which has a lot of NaCl in it. We're also going to watch a video in just a minute where they do something like this with corn syrup. Corn syrup is extremely concentrated as well.
Placed in a hypotonic solution versus a hypertonic solution. A hypertonic solution is simply a solution that has a lower concentration of solutes, dissolved substances, compared to the inside environment of a cell. For example, water is considered a hypotonic solution since it is very low in solutes. A hypertonic solution is a solution that has a higher concentration of solutes compared to the cell's inside environment. For example, water with a lot of salt is considered a hypertonic solution since it is very high in solutes. How can we examine the effects of a hypertonic solution on a cell? You might be thinking, well, I'm made out of 50 to 70 trillion cells. If I drink this, I'll know what happens to cells in a hypertonic solution. But do not do that. Drinking salt water can be very dangerous as it severely dehydrates you. Nausea, vomiting, and even hallucinations are just a few symptoms of drinking massive amounts of salt water. Ask anyone who's been stranded at sea, which is unlikely because people who drink seawater eventually died due to kidney failure. So what you really need is a lab animal to conduct your test. Darn, she's too smart. Time to try her older brother. Well, that was a bad experiment. What's a better way to test how a cell reacts when placed in a hypertonic solution? Some eggs, like chicken eggs, are surrounded by a hard outer membrane which protects the semi-permeable inner membrane. This membrane is semi-permeable because it allows substances to leave and some substances to enter. In particular, the semi-permeable membrane allows water to both enter and leave the cell, but large molecules, like salt or sugar, are too big to pass through. The question is, how can we examine the semi-permeable qualities of this inner membrane with the hard eggshell in the way? Dissolve the outer shell by placing an egg in vinegar. Vinegar has a chemical called acetic acid. Eggshells contain calcium carbonate. When calcium carbonate in the eggshell comes in contact with acetic acid, a chemical reaction occurs. Calcium carbonate will break down to form carbon dioxide, water, and calcium acetate, thus dissolving the calcium carbonate shell. Within seconds, you'll see bubbles form. These bubbles are carbon dioxide that are produced when acetic acid breaks down the eggshell. Within 3 days, you should have a semi-permeable membrane, free of the hard outer shell, to conduct your experiment. Before starting our experiment, we will first mass our egg using a scale. Egg A has a mass of 94 grams. Egg B has a mass of 103 grams. Egg A we will place in a hypotonic solution, water. Egg B we'll place in a hypertonic solution, thick and sugary corn syrup. Egg A now has a mass of 97 grams. Egg A increased slightly to 103% of its original weight. We can conclude when a semi-permeable cell is in a hypotonic solution, water will enter the cell. Egg B now has a mass of 59 grams. Egg B decreased to 57% of its original weight. We can definitely conclude that when a cell is in a hypertonic solution, water will leave the cell. In fact, this is evident by the layer of water sitting on top of the corn syrup. However, 103% change in mass is not very significant. So how about we try this experiment again, but switch the eggs? This time, egg A is going in the hypertonic solution, which is still on the right. Egg B is going in the hypotonic solution, which is still on the left. After several hours, mash your eggs again. Egg A went from 97 grams to 55 grams. Egg A has decreased to 57% of its original weight. Egg B went from 59 grams to a whopping 105 grams. Egg B has increased in weight to 177%. From this experiment, we can definitely conclude that when a cell is in a hypotonic solution, like water, water enters the cell. On the other hand, when a cell is in a hypertonic solution, like corn syrup, or more realistically salt water, water will leave the cell. Now that you're done with this experiment, time to play with those shellless eggs. No! You're just gonna...
They are super awesome, yes. It's really crazy to see what those red blood cells start looking like when they spill their guts or when they start to crenate. All right, so other questions or comments? See, I saved the best for the last day. Oops. Okay, so I got one more video for you, which again I think is a pretty fun video. There we go. All right. So any questions on the hypertonic, hypotonic, and isotonic solutions? All right, so moving on, next thing we're going to talk about are colloids. So every once in a while at the beginning of the semester, we're talking about our states, our solids, our liquids, our gases. Someone's like, hey, what about Jell-O? Is Jell-O its own state? And sadly, it is not. It seems like it should be, but it is not its own state. It's actually a mixture of solid and liquid, and it's got solids suspended inside of the liquid. And that's what a colloid is. So a colloid is made of suspended particles, and if you were to hang on to this Jell-O for long enough, eventually the solid would fall down, and then you would have your liquid and your solid separated again. The difference between colloids and what we call a real solution is the particles are larger and they tend to be inconsistent in size. So here our colloids are made up of particles that are about 1 to 1,000 nanometers in size. And we have a lot of colloids. So more than just Jell-O, we have things like fog, mayonnaise, the Jell-O that you see. So basically when you're looking at something and it is opaque, you cannot see clearly through it, those are usually colloids. So here is just a couple images of the difference between colloids, which we can call a colloidal solution, and a true solution. The true solution, the particles are less than 1 nanometer, and the reason they look transparent to us is because the light can go straight through them. It does not bounce off those particles, whereas in the colloidal solution, the light comes in and it starts bouncing off of all these various particles. Whereas again, in the true solution, the light goes right on straight through. It doesn't seem to hit those particles. Let me draw my light a little better. So it seems to go right on through without really interfering with the particles. Whereas in this colloid, it just keeps bouncing in different directions. And that leads to what we call the Tyndall effect. So if you have a directional light, and here they're using a flashlight, that flashlight's not really as good as a laser light. So sometimes when we do this experiment, we actually use the laser pointers that instructors use to point at the board because it's very directional. So if I were to take a laser light and shine it through my water, it should pass right on through. Whereas if I had something like milk, if I had something like fog in a glass, what I was thinking of is milk, Jello, something that is not transparent, you start seeing this effect right over here. And this is the Tyndall effect. The Tyndall effect says that as you shine the light through, it just kind of goes everywhere. And if you've ever tried to use your high beams when you're driving in fog, you will notice that as well. And I see a question, is obelec a colloid too? Let me take a look at what an obelec is. Non-Newtonian. So that's a slightly different. It's a slightly different theory for the non-Newtonian fluid. So non-Newtonian fluid, another really fun thing to do at home. You don't even need kids. It's so fun for adults, although it's very messy. You take cornstarch and water, and the idea is that when you put force on it, it's harder, and when you don't put very much force on it, it basically acts more like a liquid. So when we've done this before at like science fairs, you make it into a ball and then you throw it to someone. They have to catch it and throw it on very fast. It's like a hot potato. If they leave it in their hand, it starts dripping through their hands like liquid. Likewise, you can put it in a pan and have kids hop through the pans, but they've got to hop fast. If they let their feet just sit there for a moment, they will sink in as if they're sinking into liquid. But it is really, really thick, so thick that you really don't have light showing through it. But it is super fun. On the Ellen show, they took like a bathtub size amount of this and they had people run across it. And the deal is that if you didn't run fast, it became quicksand and it literally would like swallow you up. So they had people there to help to rescue people just in case. But they got some people from the audience to just run across this like little swimming pool or bathtub full of it as fast as they can. It's quite a lot of fun to play with, but very, very messy. If you do it with at a science fair with little kids, make sure you have a hose nearby. But good thought, Jervin, though. I guess I'm going to say it doesn't have the Tyndall effect because it's got too many particles. But could you call it a colloid? I'd have to think about whether you could really call it a colloid just because the particles are large enough that you can't get the Tyndall effect. We tend to say the colloids would have the Tyndall effect. I'd have to think about whether you could really officially call it a colloid or not, but I know it wouldn't have the Tyndall effect because you're not going to see the scattering of light. Sorry, I couldn't give you a better answer. All right, so here again is that Tyndall effect. So when you see a sunbeam coming through, that sunbeam is bouncing off all the little particles of dust. So that dust becomes a colloid as well. So next time you're taking a stroll with your significant other or you're just walking down the street with your family, someday over the rainbow after we're all allowed out again, and you see a beautiful sunbeam, you can say, hey, did you know this is the Tyndall effect? And they are going to think you are so very smart. So there's another type of colloid, and that is a micelle. So sometimes we have colloids that dissolve by forming micelles. And this micelle is formed from a very special type of molecule. And those of you who've had biology may have seen something like this in your bilipid layer. So here we have what we call a hydrophilic group. So hydrophilic means water-loving. And over here, we have hydrophobic. So this area down here is a group that hates the water. So normally this is a carbon group. Sometimes we call it a carbon tail. And over here, usually this is going to have a polar end to it. So a lot of times it's going to have an OH group so it can hydrogen bond. Now when you put this into water, all of the hydrophobic tails are going to tuck right inside here. So what they're trying to do is form not just a circle, but an entire sphere where they can protect their little tails that hate the water, so their tails don't have to get into the water. But the polar ends over here are out, so the polar ends can get into the water. And where we see this is actually in our soaps. So this is kind of a crazy thing. Next time you're washing your hands, you're washing your hair, this is actually what you're putting on yourself. So on the outside is the water-loving area, and that is what is going to mix very well with the water that's coming through the shower. It's coming through your sink. On the inside here, though, this is the oil-loving portion. This is the portion that is non-polar. It loves oil. So you put this soap on your skin. If you have oils on your skin, that oil is going to get surrounded by these little tails. And then what we call these heads over here, they are so attracted to the water, they're going to run down the drain. So this micelle is great for soap because, again, the tails surround all the water molecules, all the oil molecules on your skin, whereas all of the heads there carry it into the water and let it rinse down the drain. Now here's what it looks like in 3 dimensions, and I know this is kind of a freaky picture. It kind of looks like a sea creature. And the idea is that that oil molecule is going to get, right in here. So it's going to capture the oil molecule. And then the purple part, which is the hydrophilic part, this part over here is attracted to the water and it's going to rinse down the drain. So I don't want to freak you out because I know sometimes you look at that and you're like, oh my God, I'm putting that thing on me. To me, it looks more like a blackberry or something, but that is actually what's in our soaps. So just a fun application of colloids. Is that dangerous for me? In terms of soaps, there are some soaps that are environmentally friendly and there are some that aren't. So if you're going backpacking, they always ask that you be careful which kind you use because you don't want to put a lot of the commercial soaps into a natural body of water. So in terms of dangers for the ocean, there are some, I would say probably a lot, that definitely are, and there are some that aren't. All right, other questions so far? Let me see if I can find one more thing really quickly for us. I usually pronounce it a micelle, but the biology teachers might have a slightly different pronunciation for it. I almost want to say they call it a micelle. I usually refer to it as a micelle, but I could be slightly off there. Okay, so let me show you one more hopefully fun thing. Oops, hold on. Okay. So here is what Jervin brought up, and this is kind of a fun video. Every science video is fun. What am I talking about?